Welcome back, Precalcsters! Today at the start of class, we're just going to blast through the assignment from the weekend with 9.2. This is the last of the matrix stuff that we're going to see. On number 8, I am looking for the ordered pair -1, 2. Negative? Sorry? Oh. It's a Robert pin, yeah. Well, it's a Bobby pin, right? And Bobby is short, or, well, I don't know, the creator of the pin, I think. I don't know, I'm just trying to make it up as I go. Yeah, I decided this morning that I can either have my hair like super crunchy with a firm hold, which hair products are really expensive on this island, or I'll just put a bobby pin in my hair. So, bobby pin it is. -1, 2 is our answer on number 8. Okay. The good news is that no matter what your answer, you can always check it. Not because it's an odd, which it's not. You can't check this in the back of the book. But you have a system of 2 equations, which are both true for that ordered pair. Okay, number 10. Throw it out there. What do you got? 7-5. Spoken with confidence and conviction, which means you must have checked your point, and you were confident in that. I didn't hear much. You can just agree. Yeah, cool. Awesome. All right. Number 12, things get lovely. Do you have fractions or decimals? Oh, gross. 1.6 and -8.3. Hey, did anybody keep fractions? Oh, no, never mind. It makes much more sense with decimals because you're typing this into your calculator. Cool. All right, number 14, starting with the big dogs. We don't get an ordered pair anymore. We get an ordered triple. What are my x and y and z? 5, 8, -2. Love it. Okay, do me a favor. Yep. Make a peace sign so that you can have a 90 degrees. So it's not really a piece. You just got to rotate your fingers. You got it? Okay, keep them there. Now, split the difference so that like you're aiming at halfway between somebody so it's straight out. And give it the old thumbs up. Check it out. We have X and Y, right? That's our first fingers. And now we have Z. So this point, depending on where you pick X and Y and Z to be, we can work it out. So check it out. We'll just say from your perspective, let's say here's X, and here's Y, and here's Z. So this is X, positive Y, positive Z. So here we are. We're at the point 5, so I'm going to go out 5 on the X axis. And then we have 8, so I'm going to go 8 in the Y direction, so I'm out here. And then -2. Says they go down 2 in 3-dimensional space. So that point is like out here.
So Z is like depth.
Z is depth. Yep, 100%.
How would you draw that? I'm just curious.
Me personally, terribly. You could. When you sketch a system or when you're graphing 3 dimensions, and realistically it's usually done on a computer, 3-dimensional graphs, when I draw them, look like this. And that's coming out toward us. So X, Y, and Z is typically how I do it. So if I wanted this point 5, we'll say there's 5, and then it goes out here to 8, where there's 8 on the Y scale. And then this is where we run into trouble with just a point. I now have to lift this point that's in this 2-dimensional flat space out here, right? So there's a plane going out, that's the XY plane. And now I have to lift it up, or down 2 units in this case. I'm going to pretend it was +2. And here's the issue, because just on paper, I can't tell the real height of that, right? You can't tell if that's at no height or where it is. There's an issue with 2-dimensional figures. Now, when you get really good at it, just because you've piqued my interest in thoughts, saccharide comes from Greek for sugar, just in case you were also curious about that. What was I talking about? 3-dimensional, 3D saddle, calc. They probably do, but we're not going to take the time. So here's what a real graph looks like in 3 dimensions. And you can see like they curve the surface so that you can see the like orientation of it, right? This is just a saddle is what that is. It's a pretty common thing that you see in like a Calc 3 class. It can be tough to envision them, which is why we typically just use the mathematics rather than actually graphing them. Cool. All right, back to this though. That's a great question. Finally, number 16.
We did this one together.
We did. What did we get? We started it together. We didn't finish it.
Oh, yeah. 2, 3, and 5.
0, 3, and -2. Baller. I don't really want to take it, but I will. Cool. All right, please. Number wrong. Name on top. Matrices. Huge time savers. Anybody who's possibly going into graphic design with an emphasis on animation or into computer science or computer engineering, this stuff will show up again. Same thing if you just go into any type of engineering. There's a whole class focused around this idea called linear algebra. All right, just a reminder, I didn't count the phones, but I can real quick. Thank you. 2 and 5 and 4 are 9. 2 and 3 and 4 are 7. I'm missing 2 phones here. 1 phone here, I believe. And then beyond that, just a reminder with headphones and stuff. During a lecture, I would like them out. I'm going to check, because I'm sure I'll hear about it one way or the other. During homework time and such, I'm not going to let you like take your phones out and back to your desk. But if you have music in your ear and you prefer it while you're like working on an assignment, homework and stuff, I don't have an issue if we take like a minute break for you to come and put a playlist on to put in your ear. Not during lectures, okay? Cool. So, today we're going to get tricky with it, which is pretty cool. Now, the weird part of this, and I don't know if weird's a correct word, we've already seen a bit of trig. And not a ton necessarily, maybe more than you recall. That was weird. How'd I miss you? Huh. Well, thank you. Okay, where have you guys seen a bit of trig that I'm referencing? Physics. Almost everybody in here has seen it. With the understanding that we have a few people in class who don't take physics with me this year as well, which means it might feel a little bit slow for a couple people. What have you guys done with trig? What do you remember doing last year in Algebra 2? What can you tell me about trigonometry? So, Katoa, that's not something you learned from me. The Lakota chief story probably is, but you guys had seen So Katoa. What else can you tell me about trigonometry? Did you guys graph sines and cosines and tangents last year? Okay, so you've by hand possibly. We'll see. Have you graphed these? Okay, so I'm good with that. Is this sine or cosine? Looks like sine to me. You had a 33% chance. There's a reason that I think it looks like sine. You could make a claim that it is cosine and be correct, but you'd have to justify a little bit more. Okay, what else is trig about other than apparently a wave and sine, cosine, tangent? Talk it out, 30 seconds, give me something. What else do you remember? Anything at all from trig, as detailed or lacking detail as needed. Okay, so trig is triangles. You're like, honestly, that's like 80% of it. Okay, as we look at this, we are going to look at the first of our trigonometry section. Now, historically, this is chapter 4 of our textbook that we use, and normally I used to teach this just in sequence, everything went in order, but remember we just knocked out 2 chapters out of order. The reason I do that is there are 3 chapters within trig. There's the intro to just the basics of the algebra side of it, and then from there we'll move into, away from rather, just the pure algebra side into some identities and a bit more algebra realistically. And then there's the application stuff. The trig that we have seen in physics this year, we won't see in here until chapter 6. Just so you guys are aware, because it's how do you use trigonometry in analytic situations, which is physics. However, we're going to jump in the first of 3 chapters to start our whole trig unit. Just so you guys know, we're going to have a chapter test and quizzes just like normal. I'm not always super in favor of cumulative big tests, but there will be a cumulative big trig test at the end of these 3 chapters. So all of this stuff is super important and will help with calculus. We're going to start with chapter 4 today. Chapter 4, and our study is trigonometry. You will never see me write this again. Write this word again. Trigonometry. Okay, let's just all agree, I don't think that you'll be wrong. Shorthand for trigonometry, That is correct. Trig. Now, just so you guys can see it, you don't need to write this and define it, but a triangle is a trigon. If you guys, I don't know how you learned it. Do you know what you call a 9-sided polygon? A nonagon. How about 11? Almost. Deca is 10. So that's a good thought. Hendeca, it turns out. Now, we all have them memorized, right? What about a 33-sided polygon? It's a 33gon. And my teacher, like Zeke's teachers, are going to think he's dumb. It's the real thing. He knows the word triangle and square, but he also knows the word 3gon and 4gon because that's the real language. I don't really care what you call it. That's just nomenclature and how we name it. If you know what it means with generalized kind of language here, I'm good with it. Okay, so in trigonometry, metric means to measure something, and we're measuring angles of triangles. The study of the measure of triangles. That's all that this is literally meaning. Now, it gets a bit more complex, and there's huge applications in the world of trig, but we're going to jump in nice and easy. Our section today is in 4.1, and we're going to talk about angles, and specifically measuring angles. Measuring angles. All right. Cool. I should probably get my notes so I don't go like too far in the wrong direction just as we're looking here. Now, what's an angle? Can you guys show me an angle? Cool. What is it though? You've just shown me. Everybody knows you could put an angle in front of you and you could explain what's in front of you. How would you define it though to somebody who's never seen an angle other than just showing them a picture or a hand gesture? I like where it's at. Let's sneak this in. We're just going to write off agree on a single angle. Now, angles. Can you draw an angle with one side? It'd just be a line, right? Like, you can't.
Good point to start at, I guess.
Ooh, if you, so all of a sudden, we can think of angles between lines, but in my mind, it's easier if we think of a vector or a ray. Just remind me, what's the difference between a vector and a ray? So does a vector. So does a vector. Like, right now, without any context, you can't tell me with certainty if this is a vector or a ray. A vector points in one direction to say, look, I'm going from here to here, right? I have a vector on the board, I get rid of that point, and I now have a ray. How far does that ray go? Forever, right? Like it just never stops. That's the only difference. Now, to talk about an angle, we need to have two sides. So we're just going to say it is the amount of rotation, to move a ray, and I'm going to say an initial side, and I'm going to underline this. And I'm going to call it a side, and the reason I'm not going to write ray here is the side of an angle could be a ray. Could it be a segment too, though? Could it be a line? Yeah, and I don't want to have to write all three of them. So we have the amount of rotation to move an initial side to a terminal side. So we have some amount of rotation to move the initial side to the terminal side about, or around if you would rather, a common point. Are you taking two sets of notes? I will make a copy of my notes. You don't need to do that. You do you. I'll give Makisha a copy of mine. I'm fine with that. About a common point. Now, called, and we're going to pause right here, and just spacing wise, I'm going to leave a blank line. And I just want to make sure that we can draw this. Now, when we go through here, we're immediately going to jump into something. But right off the bat, if I want to draw this picture, here is a common point that both of these are going to share. Here I have a side in the form of a ray. Here I have a side in the form of a ray. What I have given, can you tell me which one was initial and which one was terminal? Not yet. Now, that's okay. It doesn't really matter here. If we call this one side, there's an amount of rotation, either this direction or this direction, that one would need to go to move one to the other about that common point. What's this common point called? Love it. About a vertex. Now, vertices is the plural of vertex. But there we have it. Cool. That's it. That's all an angle is. That's how we define it. Now, beyond that, just some key features and some conventions. So, standard convention. And these things you've seen, so I'm going to kind of gloss over them. If it's way too fast and you don't get one of these, or you have issue or don't recall, please let me know so I don't just keep like blasting through them. Okay. Normally, we rotate which way to be positive? Rotating counterclockwise. And I'm going to only write this one as well. Counterclockwise. Or anti-clockwise, you may see it in other places. Rotate counterclockwise, which, just for future reference, CCW is going to be my shorthand for counterclockwise. For positive angles. Okay, I think that it's implied just by this statement. But if counterclockwise produces positive angles, then clockwise would do what? Negative. Do I need to write that? Cool. If you want to write it, you are welcome to. Negative angles go the other direction. Okay. Typical, we use letters to represent angles. Typically, if you think of an angle, and physicists, you're going to be much better at this just by virtue of how much practice you've had. What letter do we use for angles? Theta. We use Greek letters. Typically use Greek, and that should be capital, Greek letters as variables, as angle variable. Okay, I'm going to get real tired of writing angle. Anybody have a shorthand that they know of? Angle. I would encourage, if you don't do it normally, put the arc going across this angle, because otherwise it's going to look like an inequality. Let's avoid getting goofed up. Shorthand for angle right here. Okay. Beyond that, hook it up. We normally use theta. Looks like this. Are there other Greek letters that you can recall? I know we've gone through all of them. Ooh, this is theta. What did you say? Zeta. We're not going to use zeta. We use phi. I like to use phi. This is the golden ratio. It's less common as an angle, but you could. Alpha is pretty common. Beta is pretty common, which is like a capital B with a tail. And if we need more than this, we'll recover some. But it's probably going to be one of these four. Okay. Last little piece that we're going to say by convention. On coordinate plane, or the Cartesian plane, where would we normally put the initial side of an angle? Where do you start measuring? So 0 is, I like it, depending on what you mean by it. I can't say I start at the origin because it has to be a side. So right now, if you, I'm going to put a, you're closer. Huggins said X. And you're so close. I think you probably have it right. You do not need to sketch this. But if I wanted to draw a 30-degree angle, does it bother anybody if this is where I naturally put my 30 degrees? Like, is that kind of annoying? It's like a lot annoying, right? Why? There's a lot of stuff that, like, that's an arbitrary spot to start, right? Where should I start it? This is my initial side, because if it's positive, it must be going that way.
Where y is 0.
I like that. Where y is 0 on the x-axis, let's put them together, the positive x-axis. On the Cartesian plane, the initial side of an angle is normally unless we specify for a particular reason, normally the positive x-axis. Okay. Boom. One more little definition, and then we get to start doing some stuff and hopefully either recalling or learning the better way to talk about angles. Okay, last little thing. And I'm going to sneak over here. It's not really one of these conventions, but it's just an additional vocab since this is the very first lesson of the section. Okay, when you see co in front of something, what does it mean? Like to cooperate with somebody. You're working with somebody else, right? Together, you're operating together is literally what it means. Co, together, cool. Cooperate. Now, as we look at this, if we define this real quickly, we're going to sneak in coterminal. Now, we already know that the co means together. What's terminal? End. So, in literal translation, what would this word mean? Coterminal. Ending together. Coterminal angles, they simply have the same initial and terminal sides, but we have a bunch of different rotations that can make that happen. So we'll just say have same initial and terminal sides. And we'll dig into that here shortly. Terminal sides. Okay. So, and I'll do it up on the board. I want to do it with my hands and arms and stuff to get crazy, but there's people that can't see it. Maybe. Nope, we'll just do it. Okay. How could you make coterminal angles? Like, you don't need to sketch this, it's just us talking. Let's say I have an angle that starts here and it ends here. How on earth could we make this coterminal? Like, I see infinitely many angles up on the board right now, and even infinitely many if I'm just looking at this. So that's theta. How on earth could we have another angle that starts and ends at the same spot? Hey, you could just add 360. So, I'm going to do this one with yellow. I'm going to keep the orange as my initial. If I start here and I rotate theta, if I go 360 what? Degrees further, I just end here again. How many times can you add 360? So there's half of them, which seems weird because I just said that infinitely many angles is half of these angles. There's another way to get there. Any number of full circles will end me up there again. You could subtract. Now, I don't know if this is exactly what you meant, but it's going to wrap around to being the same. Instead of going in the positive direction like so, could I have gone this way and ended there instead? Would that start and end at the same spot? Boom, coterminal. Okay, now with that, that's all fine and dandy. Nothing crazy there. We will work with those. But right off the bat, we are going to ditch the wrong way to think about angles with the understanding that there's not really a right or wrong, but there's a better way to think about angles. We regularly measure, if I say, hey, this angle is 15, and I just corrected Rafa a second ago, what's the thing we were missing? Degrees. Okay, what's a degree? 1 degree. How would you explain what 1 degree represents?
Like the size of rotation.
Okay, so what would 1 degree mean?
Size, but like
The amount. I'm okay with that.
of rotation, yeah.
So what would 1 degree of rotation be?
Just the velocity, or I don't know, it's a little tiny bit.
It's a part of a circle, right? Because if you rotate, eventually you're going to make a full circle. How much of a circle is 1 degree? 1/360th, right? Okay, I can't recall if it was this class or another one. Why 360? One more time. So it does, but like, why did they decide 360 degrees was what makes a full circle? Why not 500 degrees? Or 100 degrees if you were in the metric system? Like, it's just a choice, right? I wasn't there when it happened, I don't think. When people first started formalizing mathematics, 360, it turns out, has a lot of factors. It's easy to divide 360 into parts. That's the reason for choosing 360. A further explanation, without going super into detail, because I don't know if it was in here or is in our other class, if you count differently, we can count to 60 on our hands.
I think you told us.
Was it in
both
here or
classes.
physics?
I think you told us in both classes. Maybe.
That makes sense. Can somebody tell me just how briefly? Count the creases on your fingers, right? 1, 2, 3 on the first finger, 4, 5, 6 on the second. There's 12. Put up a finger here, and now you can get 13 through 24, 25 through 36, 37 through 48, and 49 through 60. And we can count to 60 on our fingers. Okay. When this math was getting worked out and first formalized thousands of years ago, that was a choice. Now, if aliens exist, which I'm not confident, but I am leaning towards yes in my personal opinion, they would not probably pick 360 because maybe they have different fingers or just a totally different thought process, which means our math wouldn't line up with aliens in that sense, right? Like pretend we had another alien civilization that looks wildly different. They speak English for some reason, or they have translators, and we're trying to talk out math with them. This is going to be a point of confusion between us. Now, the cool thing is that it doesn't have to be. I don't know why this is the one that naturally sticks when we talk about teaching people math. There's another way to measure angles. We'll talk about degrees here soon. What's the other way to measure angles? Radians. So, how many of you remember hearing the word radian? Who can tell me what it is? Cool. Well, let's dig into it. So, for our second main section, we've talked about how do we measure them and all that basic stuff. Radians feel unnatural when we talk about them. However, these ones are not just man-made or human-made. This is the way that angles could be measured no matter where in the universe you are, that we would all get the same thing. We don't have to pick some arbitrary number. Now, you guys remember dealing with radians, I think. Or you at least remember seeing them. Can you tell me anything about them? Something with pies in it. Do you guys remember doing that last year? Did y'all do the unit circle? Do you remember it? Okay, that's fair. Okay, first thing, challenge for you, and I'm going to pause because I don't want to reveal secrets. You're going to draw a Cartesian plane, and you're going to put a circle whose center is right on it, right at the origin. Okay, it doesn't have to be perfect, but you want it big enough that you can write and talk about stuff on your circle. So I'm going to cheat and use Desmos to get a circle. Bless you. All right, so here's my perfectly drawn, bless you again, perfectly drawn circle that I did all by myself. But I can't move for some reason. I don't know why I can't move it. Move. There we go. Okay. Here's a circle placed on a coordinate plane where we have a center point at the origin. Now, anybody have a perfect circle on your page?
Never.
Okay. Some of you may have a kind of close one. I wish that I had. This is pretty close to a perfect circle, roughly. Okay. Now check this out. If I wanted to, and I might make you guys stand up, and I should probably show this here. Let's see if I can get the camera up. Hello. Okay, we have a circle. Do you guys agree that roughly here's the center? Now, there, I'm mirrored. Okay, from this, if I measure a particular segment starting at the center of my circle and working outward, what would I call it? Ooh, one more time. The radius. So I'm going to do just that. Now, I'm going to do it somewhere up arbitrarily here for just a second. And it's going to seem like I'm just randomly picking, and I am, sort of. It's in quadrant 1. I'm going to call this the radius R. I hate how bold it is. Cool. Do you guys agree that from the positive x-axis, this formed some angle? Now, we don't know exactly what that angle is, but we can call it theta. Are y'all cool with this? Now, here's the cool part about this. And I'm going to go back to the video. If I measured the distance from the center of the circle out, I think that I could probably represent it with a piece of string. Now, it's not going to be perfect, and I think the other side of the string is less frayed because I burnt it. But do you guys agree that as I'm looking here, this is my radius, roughly? So I can't let it go, but it's there. Everybody agree that that's pretty close to a radius? Okay. I'm going to mark that spot just so I can pick it up. Now I'm holding a radius. Okay, I'm physically holding the radius. It curls up on itself, but this is the distance that I just measured. Everybody cool with that? Now check it out. On my circle, if this is x and y, just like normal, it's just oriented, is there somewhere on this circle where the length that I travel around the outside is exactly equal to the radius? Now, for this, if I go back to the picture, you guys can physically see it. I wish I had string and stuff prepared for this. But let's look at this picture again. There is a distance somewhere along this, all the way around the outside of the circle, where this arc length, and we're going to sneak this in and we're going to learn a pretty common letter, the arc length, which we'll call S, like it varies as I move that radius, right, as I go through different angles. There is a situation where whatever angle I go through produces an arc length along this curved path that's exactly equal to the radius. Before we move on, let's just make sure that makes sense. This angle, and whether it's this one exactly or not is a different question, but this angle, theta, that we're talking about right now, is the angle that I need to make the length of this arc, this curved path, exactly equal to the radius. Okay, everybody cool with the fact that that exists? Now, it turns out that if you're cool with that, we are golden. And the idea of a radian is going to make a little bit more sense. They feel unnatural at first, but we'll get enough practice over the next 3 chapters that hopefully you guys think in radians rather than degrees eventually. Okay, we're going to sneak in a definition. And I hate where this is written, but we'll just do it here. The angle theta that makes an arc whose length equals the radius. I'm going to let you guys catch up because that's what that picture we just saw. The angle theta that makes an arc whose length equal to the radius is exactly 1 radian. It's not usually caps here, but 1 radian. And I would use a number, but I just want it to be really clear. Okay. That's it. Now, we get a nice mathematical relationship out of this. What this means is if we let this radius be something nice, like, I don't know, 1, what we would wind up seeing is that in this situation, and we'll just go ahead and make that if r equals 1 comment, if the radius r equals 1, then, and really it's for any of them, but this is easier to think about, then we get a nicer relationship. I think theta would just be equal to s over r, which would be equal to 1 over 1, right? Because the radius is 1, and so must the arc length be for that theta. What if the radius were 10? 1 radian would be the point on the circle where the path through here was how long? 10. No matter what you do, what is the arc length s over the radius always going to give us? 1, and that is 1 radian. Now, to go out further than this, there are pieces that we can do. We can either just blindly trust the picture and we can look at it, and I'm fine with doing that. Or we can kind of go back a different direction. I'm just going to copy them and paste. I'm going to eyeball out, and you don't have to draw it on yours, but this is 1 radian of rotation so far. If I go 2 radians, you guys tell me when it looks like I have congruent angles. So depending on where you're looking, does that look about the same theta? Would you guys believe it if I said between here and here is also theta? Can't tell if I'm losing people. If this were, I'm not going to give you a number for degrees. Is this amount of rotation from here to here about the same as this one? So here, and then if I don't move, I just move this. It's the same, right? Okay, there's another theta then, and we're just eyeballing it. How many radians have I gone through now? This is 2 radians. If I go a 3rd radian, I'm going to eyeball about right there. I'm now at 3 radians. Right here. This amount of rotation has taken 3 radians, because just 3 of that angle. almost halfway through the circle. Man, if only there were some relationship between the distance around a circle and its diameter or its radius. Some number that popped out anytime that intelligent species are dealing with circles. Oh my pi. It's a little bit bigger than 3, right? What's pi, approximately? That's a little bit bigger than 3, I'm pretty sure. Hey, look at this. All of a sudden, we get some awesome stuff out of the deal. Now, you do not have to have any of these other pieces, but if you are an intelligent species, pi is going to be discovered by your species. There's no way around it. You might write it differently. You might have a completely different way to write down numbers and notation and everything, but the ratio of the distance around and the circumference, the circumference to the diameter, like we caught it as human beings, any alien species that's doing mathematics is going to recognize it as well because circles are so nice. Going a step further, quick question just as a check for you guys, and this is going to be like a fill in the blank and just a little follow-up. The circumference, which give me another, what does circumference actually mean? Perimeter of a circle, right? Okay. The circumference is, how do you find circumference? 2 pi r for every circle. Every circle has a circumference of 2 pi r. All that changes is the radius r. Okay, now we already used it somewhere else, but what would be like the nicest possible radius that we can make a circle have? 1. Like 1's the easiest to deal with, right? So let's take one more step in that direction. If r equals 1, let's just see what works out. If r is equal to 1, then I know that the arc length around the whole circle, and I'm going to say a full circle, has length, and I'm going to say circumference is what I'm really going to say. What would the circumference be if the radius was 1? 2 pi. Everybody okay with that idea? Now, here's the cool part. Which of these letters in our radian definition was 2 pi? Or sorry, whoa, that was a weird little hiccup. Which of these letters represents the length of the path along our circle? Theta, S, or R? So we would get 2 pi, and I'd put a period there, but it'd be equal to the arc length. Are you guys okay with that? The arc length around the whole circle would be 2 pi if the radius was 1. Which means if we rearrange this expression from before, then I know that S, which we just said was equal to 2 pi, is really equal to R times theta. So it just implies that 2 pi is equal to R times theta. And if the radius again was 1, it would just be 2 pi, right? And did I lose anybody in that logic? Okay, so let's just make sure that we're on the same page. We're going a full circle, right? So on a full circle, the radius is 2 pi r. Or sorry, the circumference is 2 pi r. If the radius is 1, then the circumference is just 2 pi. Now, how much do you have to spin around of a circle to go all the way around the circle? That's a weird idea. Don't give me degrees, just give it without the degrees. A full amount, like a full circle, right? Which means we've just found that the amount of rotation that it takes to go through a full circle is, what did we just say that last theta was? 2 pi. This is the basis for a way to measure angles that has a connection to what really happens when you do it. None of this arbitrary 360 or whatever angle degree you want to talk about. 2 pi is the actual amount of rotation that you must make. Now, for this, we're going to just make a few different statements. A full revolution, or spin, if you will, is 2 pi, and then here's one more little part that we're going to connect it here. Always annoyed me when I saw it when I was learning this stuff initially. If we define this angle theta as S over R. Give me a unit that you might use to measure a radius. I don't care what it is, just I might measure it's 10 what? Meters. If I measured that my radius was 10 meters, what do you think the unit I would use along that path that I'm walking would be then? Meters as well, right? It makes sense it's both the same. Which means when I look at this theta equals S over R, regardless of the unit that you have, if I had meters, S meters, right? Arc length in meters over radius in meters, what happens with those units? They divide out, right? Meters over meters, they're gone. Which means, do we have any units left here? Okay, this is the weird part. In yellow, I'm going to write a unit with the understanding that radians don't have units. If you don't have any units left over when you're doing angle stuff, like no degrees or anything like that, you must be in radians. Okay, because that's such a big thing to get over, entirely optional, and we're going to get away from it at some point, radians, I shorthand with rads if I'm including the unit, but I can't stress it enough. Is there really a unit there? No. A full circle or a full revolution is 2 pi. You can just stop there, and you are completely correct. If you want to be a little bit more clear with your statement, you would say it's 2 pi radians. Okay, powers of deduction. I want you and your neighbors to work out the rest. I'm going to use fractions for this, okay? Okay, we know a full revolution is 2 pi radians. Okay, I'm just going to say the same thing, a blank revolution, but I'm going to use fractions. I want you guys to tell me how many radians is in this much of a revolution, a half of it, or a quarter, or 1/4 of a revolution. Well, that's okay. You don't even need to remember it. If 2 pi radians is a full circle, Sean, what's half of 2 pi? Oh my, pi. Half a revolution is pi radians. Okay, we're going to do a couple weird ones. So we got a full, a half, a quarter, a sixth, and a 12th. This much of a revolution is all we're after. And I'm going to give you guys a moment. I'll call on a bunch of random people. Okay, now there's a few ways you can think about this. In my mind, I think of just cutting in half and then in half again. But it's not the only way to go through this. Couple ways. Some of you guys, if I have pi radians is half a circle, a quarter circle is half of that, right? So in my mind, I just think about taking this, whatever the half was, and cutting in half again. And I'll do this in yellow. Some of you guys, and I don't know who, but several of you, I imagine, have 1/2 pi. Okay, do me a favor. Let's not quite use that. Fern, I'm going to call you out just because. When I looked at Fern's pages on a different one, he had this written. What's my concern with that?
It looks like the 2 is pi.
Oh, it looks like it's 1/2 pi, which is not quite the right thing. We are going to avoid any confusion with this. We'll come back and we'll change them. You're not going to erase anything. 1/6 of a revolution? How did you write that out? 1/3 pi? Now, it'd really be 1/6 of 2 pi, right? And that's how you got it. So you got 1/3 pi. Anybody have that exactly written on your page? Oh my gosh, I love that idea. What's a 12th? Last one. Is it a 4th? 2 pi divided by 12, or cut into 12 pieces, is 1/6. So 1/6 pi. Okay, for anybody who has these, don't erase them, but we're going to make a change, and we're all going to just agree to it. This is okay. This is better. Pi halves. 1/3 pi is okay. What's better than 1/3 pi? Pi thirds. What's better than 1/6 pi?
I don't like this one.
I'm sorry, we're going to commit to it. Like, this is going to make stuff and avoid so many errors. Cool. We're going to use this. There's not a time that you will see me write it the way that you might have done it initially. This is going to be the convention. Okay, now, with all of these things looking, we're now going to start to generalize some stuff. On your pages, I want you to underneath, let's just talk about where theta lives, or a range for theta. Okay, all I want you guys to do is we're going to define, I'm not going to write it down. When I put the Cartesian plane up here, I form 4, what do we call these? Quadrants. Now, I think in degrees it's easier, at least probably realistically this whole year. And I'm going to just be honest with you. I still think easier in degrees, even though I know that radians are probably the better way to go. I think that just as a generation, eventually somebody should just say, let's just stop using degrees, let's just use radians, so that we don't get 16 years of intuition with or degrees built up, because now we're trying to unlearn it.
Did you say that degrees are like it's arbitrary apart from the fact that you can split it up good?
Yep.
There's no reason for.
Yep. Other than that's the way it was written when they first did it, because they counted in 60s. Yep. This one is not arbitrary. This is defined by reality. Okay. Now, in degrees, you guys can tell me here, if I go a full circle, or if I start here and end here, there's 2 ways I can do that. This could either be 0 radians, right, no rotation, or how much rotation have I made here? And I got to think clockwise, counterclockwise. Okay, how much rotation have I made when I start at the positive x and I go like this? 2 pi, and you don't have to, but when we're speaking, it clears it up. 2 pi what? Radians, or you can say rads, I'm cool with that. Do you guys agree that this is 0 or 2 pi? It could be the same, right? Because you end at the same spot. Could it be 4 pi? And 6 pi and 8 pi and 10 pi? Because every 2 pi is just another full circle. Okay, we have 4 angles that we refer to as quadrantal angles. What I want you to do for each of these 4 quadrants is I want you to tell me, and we'll do this first one together, if I have an angle theta that's anywhere in the first quadrant when I draw it, it is between 2 values for radians. I know that it has to be greater than 0 radians, right? And the 2 pi part, we'll come back to it. But you agree if I want to end up in quadrant 1, I have to rotate more than 0. Because if I don't, I'm not in the quadrant. I'm on it. I'm on that line. Okay. Between 0 and what? What would this 90-degree right angle be? How much of a circle is this? That's a half a circle? You're right. I'm being facetious in probably a bad way. 1/2 pi. Or give me a better word. Not 1/2 pi. Pi halves. Theta must be between 0 and pi halves in order to be in this quadrant, right? Okay. In white, since I'm kind of putting this, I know that this is pi halves. What's this one? All the way over here? Pi radian. And this one down here? 3 pi halves. Love it. Okay. From this, I want you guys to tell me what the range of theta is for each of these remaining 3 quadrants. And they're going to be compound inequalities like this. Nothing too crazy happening. What's up? Good ones? Cool. We will start right here tomorrow at the start of class. I want you to finish these 4 quadrants. This is the homework if you don't finish it in the next 60 seconds. Also, I can come around and check and tell you if you have it over the next 60 seconds. We'll pick up right here tomorrow, though.